and in this video we are going to cover additive manufacturing simulation in Abaqus using the Goldak Flux. We are going to explain the additive manufacturing simulation process from A to Z, and after this video you should be able to complete an additive manufacturing simulation project on your own. Both the thermal and the mechanical model by using the Goldak heat flux, such as residual stress, will be used in this video. I would recommend this video to anyone who is interested in 3D printing or welding simulation. First and foremost, I explain the Goldak heat source model. After that, I will go through the description of DFLUX subroutine for a complex path. Then I throw some light on the thermal model, and after that the mechanical model development algorithm. Last but not least, I am going to explain the results of the simulations. As you can see in this formula, since the Goldak formula is volumetric, the front and the rear part of the heat flux are geometrically different. The A, B, and C coefficients are related to the geometry of Goldak Flux, and in the picture below you can see the geometry of Goldak's double ellipsoidal heat source, which consists of two ellipses. Here you can see the values put into the project. FF and FR represent the thermal ratio of the heat fluxes in the rear and front part. In this slide, a model is shown in which we can see the 4 tracks that the laser passes in order to fabricate every layer. First, a heat flux passes through the left flank. Then another heat flux passes at a certain distance from the first. The third and fourth flux follow with the same equidistant distance from the previous one. All in all, 4 tracks are needed to create a layer. Here we can see the geometrical model of each layer with a length of 2 mm, a width of 0.7 mm, and a thickness of 0.03 mm. In the picture on the right, the completed model with mesh is shown. Here we can see the top surface of the volumetric heat flux illustrated on the surface. The heat flux travels in line with the x-axis at a constant speed of 1 meter per second. It is important to keep in mind that as the number of layers increases, the center location of laser is changing. This will be adjusted in the subroutine code. In case you were faced with a convergency problem in thermomechanical analysis, a possible option to fix the problem would be using the decouple method. Since the analysis is performed via the decoupling method in this video, after we successfully complete the heat model, we need to create a mechanical model with which to predict the mechanical behavior of the simulation. To develop the mechanical model, firstly, you would need to add the mechanical properties, such as elastic, plastic, expansion, and etc., to the material. After that, you need to change the heat transfer step to the static general step. Then, you need to define the boundary conditions according to the problem conditions. The next step is to import the thermal data from the ODB file. Lastly, you will need to change the element type from thermal DC3C8 to mechanical C3D8. As you can see in the picture on the right, first a small amount of powder is deposited on the subroutine. Then the laser travels through the powder, turning it into molten liquid. Then the cooling process will be performed to turn the molten liquid into solid. After that, once again, the process is repeated. Some powder is applied to the layer. The laser travels through the powder and makes molten liquid. After cooling, the liquid turns solid. Another layer of powder is applied, and so on. The picture on the left illustrates the heat spreading due to the track left by the laser. We will show the 4 tracks later in the video. In this picture, the tension caused by the laser passing through the subroutine is also visible. At At first, when the laser has not yet reached the desired point, the temperature is very low. When the laser reaches the desired point, the temperature experiences a sudden rise. And as the laser passes the desired point, the temperature falls once again. The process will be repeated for every desired point that is in the path of the laser. Here we can see the tension against time graph of the desired point. As the laser progresses, the tension of the point undergoes changes. To grasp this graph better, I will juxtapose this graph with the temperature against time graph at the end of the video, so stay with me for the comparison. For residual stress, we can explain that it is generally created when the material is under manufacturing processes, such as extrusion, bending, attraction, and rolling changes the shape. Residual stress can be both advantageous and disadvantageous. For instance, if it creates tensile stress in the material, it will reduce the fatigue life. If you are interested in predicting the fatigue life with FE-Safe software, please refer to the link I have put here.
Let's introduce Salman Hosseini. Salman brings extensive experience in Abaqus with more than 400 successfully completed projects, including fracture mechanics, composites, additive manufacturing, biomechanics, and beyond. He leverages advanced simulation solutions coupled with Python scripting and Fortran subroutines. Salman offers free online consultation sessions tailored to graduate students, professors, and industry experts seeking to learn modeling techniques. With over 200 hours of tutorials and having mentored over 100 students, he is dedicated to helping you with your research, education, and industry-related projects. Contact someone today to schedule your free consultation, discuss your project, and confidently tackle its challenges.